Welcome to the N64 Reverse Engineering Masterclass. I'm your host, Kaze Emanuar, and you might know me from a YouTube channel where I reverse engineer N64 games and I make a lot of mods. I actually hold the world record for the most games taken down by Nintendo, which is a title I could do without. I'm here today to teach you how to do the reverse engineering of any N64 games. We will be using Mario Party 64 as an example, just because I think that's a game everyone knows, and it's not really been modded that much, so I think it'd be really cool to just, look into it. I'll teach you the basic tools that we'll need to do this, and I'll teach you some basics about assembly programming on the N64, which is actually really simple, so don't be scared. You will be learning how to assembly hack Mario 6 and Nintendo 64 games. Mario 64 as well if you want that, but it's pointless. And we'll be looking into mostly Mario Party 64. By the end of this, you will have the ability to properly annoy the shit out of Nintendo. First of all, let me show you the tools we'll be using. Our first and most important tool will be Project 64 Debugger. Project 64 Debugger is a tool that allows us to look at the code while the game is running in real time, right? So here we can see the assembly code. Don't worry about this right now. And here we can see the memory as well. That's the memory search. I want the viewer right here. We'll be using the search as well. So for example, I randomly just already know all the variables here. But let's say we have Mario and we wanted to make changes to Mario. That's the wrong address. Here we go. Right, so we see a bunch of variables here. This one here I know is his health. We change that to that, you see? And we affect the game. Just like that. Or if we wanted, we could even set like a breakpoint. Like, let's go to the water. We set a right breakpoint. And we see right here in the code that right here Mario's health gets overwritten. So if we wanted, we could like go to this address of the code. We could turn it into a nub, which is just a bunch of zeros. And now Mario can no longer drown. Because what we just overwrote was the part where the game makes Mario drown. And that's basically how this tool works. Our next tool is LemASM. LemASM looks very similar to this, right? This was our RAM code, but LemASM shows you the code in the ROM, which is the code that you would get if you dumped your ROM through any legal means and stored them onto your PC. You open it in a hex editor like this, then, so you can see same numbers here, but it basically interprets this hex here for you as assembly code. Real quick, when you open LemASM, you want to press F6 and F7 once, so that you get into the right mode where it actually shows you the assembly code with the correct register names. But I'll be going into that more detail later. Next tool, also very important, is Kaze ASM or RMaps. They both do the exact same thing. They both look the exact same. The only difference is that RMaps is objectively better. Kaze ASM has a bunch of bugs. But I'm so used to Kaze ASM that I'm using this. If you are following this along at home, please use RMaps. Don't use Kaze ASM. And obviously, it's gonna be helpful for us if we have some documentation about how the Nintendo 64 registers work. So we got like the Ultra 64 website, and we got this little N64 programming wiki book, which is also helpful. We'll be using both of those, and I'll leave a link to that somewhere so that if you want to do more N64 programming, you can follow along. Now, we are not here for Mario 64, we are here for Mario Party. So let's go into our emulator. This is where we actually start programming already. We are past the introduction. We're now actually gonna go and hack Mario Party, figure out new things no one has done before. Here we go. One thing real quick, if you are in Mario Party and you open the emulator, please go into your settings. And under advanced, you want to enable the debugger, so you can actually open these windows here. And you need to use the interpreter core. Basically, the way emulators work, they have two modes. The first is recompiler, which takes a look at the assembly and it compiles into slightly more efficient Windows code. And interpreter, which interprets the assembly line by line, kind of like Python code does it, you know? And using the interpreter mode is required if you want to debug. Unfortunately, that means the performance is going to suffer, and this is going to be absolutely miserable to click through. But we'll live. Yeah, you can see it's like super slow. I have a modern PC, and interpreter is so slow we can barely even run it at full speed. I just had to clear the breakpoint because that breakpoint was still there from my Mario 64 debugging there. So our first code is gonna be a 999 coins code. We're gonna go into Mario Party and we're gonna cheat 999 coins, and we're gonna make this a Game Shark code. Basically, a Game Shark code is, you know, there were like special modules that you could put onto your cartridge, and then they would activate cheat codes for you. So if you go into System, Cheats, Mario Party actually comes bundled with a bunch of them already, right? We're just gonna add onto it and give you 999 coins. Let me just get into a game. So the basic way we're gonna do this is we're gonna look through all the memory. We're gonna find the variable that stores the coins, and then we're just gonna overwrite the variable with a higher number. Very simple, very basic. So while this is loading, we can already open our menu, debugger, memory search. And let's reset this. So let's think about this. What's the value type gonna be? Well, we know you can get more than 255 coins in Mario Party, so it's at least an N16, right? So we can already do that. We know that we start with 10 coins, so let's already put that in. Let's roll our die. We're gonna go third. It's gonna make this video a little longer. Or this lecture. But we can live with this. Alright, we got our 10 coins. Let's search for the number 10. We have 2,211 results. And one of these is gonna be the number of coins we have. But obviously that's not good. We can hit search a few more times to like cut out a few variables that would have changed. Alright, we've hit search a few more times. We've gotten it down to 1,700 results from variables that would have changed. Now it's our turn. Let's make a save state here, which is the F5 button. And let's just do something random that will modify our coin count. So this will change it to 13 because we land on the blue space. We hit search again. There's only 3 variables that are set to 13. Ooh, that's good. Now, we can just brute force it. 800D464. Wait, what? 800D8464. Set to 0A. Set it to 16. Okay. This is not where our coins are stored, right? As soon as we change this variable, it gets overwritten. So this is probably like some temporary display variable. Let's just go to the next one. 800F3318. Set it to 16. We have 16 coins. Oh. Set it to 1,000. Actually, this is... Oh, no. That was 999. Alright, we have our 999 code. Now, if you wanted to make this a cheat code, which, you know, is very simple, we go to System, Cheats, we add a no cheat code. Oh my god, how does this work in this? No cheat. Have 999 coins. So, the way Game Shark codes work, they have a prefix, which is like 2 random numbers, and then they have a rem address, which in our case is 0f3318. Space 037, which is the variable. Now the prefixes that we will most commonly use in the Game Shark code are 80, which means write byte, and 81, which means write password. So if we have this cheat, 999 coins, then as soon as we load our Game Shark, our save state, see, the Game Shark code will overwrite it. And if you had a Game Shark module, which I am not sure how many people do, you'd be there now. Or, you know, you can just use the Project 64 thing. Now, let's do something more complicated. Obviously, finding a variable, not that difficult. Let's do something that will require a little more skill, and that is, we'll modify code. Code that will do things. Before we can move on into more complicated stuff, I gotta teach you guys how to code an assembly. Our final goal is to import our own custom model and to make some code changes to Mario Party. And both of those will require a lot more assembly knowledge than what I've taught you so far, which is basically nothing. Usually learning MIPS assembly would be like a university semester, I think, but I'm pretty sure I can teach you in just 30 minutes enough that you can do this. I say that programming without knowing assembly is like painting without knowing colors, so even if you're not planning to reverse engineer, I think this is going to be very important for you if you don't know MIPS yet, or you don't know any assembly language yet, rather. MIPS is actually the easiest to learn because MIPS on the N64 is a RISC architecture, which means reduced instruction set computer, which means there's only very little you need to learn to do everything. In fact, there's like 50 commands at most, and they are all super self-explanatory. Let me show you an example. Let's say we want to set Mario's health to 0, right? We do something like Mario health equals 0. That's our line of code that we want in assembly. Well, this is just something we know. We know Mario's health is stored at 8033B21E. Now in assembly, it's not about like variables and stuff. It's about manipulating memory. Instead of a pointer, you just have a memory address. Instead of variable, you have the contents of a memory address, right? So our goal is going to be to set this value here to 0. How to do that? Well, first we're going to do Louis 8033. What does this do? Louis means load, upper, immediate. Like I said, super self-explanatory. Every comment is named exactly what it does. So this sets 80 equals 8033, and because it's the upper immediate, we add 4 zeros. Next, ORI 8080B1E. ORI means or immediate. So 80 is going to become the result of 80 ORed with B21E, which means 80 is now B21E, like this. And now we just need to store 0. And that is also very easy. SH, store half word, aka 2 bytes. R0. R0 is a special register that is always set to be exactly 0, which is really used for us. 000 from 80. We store the value 0 for 2 bytes at 80 plus 0. Technically, we didn't need this line of code here, and we could have just, put the B21E here. So Mario's health is now 0. That's the basics of it. And now I need to explain what the registers even are, because not every register is the same, as you've seen from the R0. So let's go into our register list real quick here. You see a bunch of stuff. AT, V0, V1, A0, A1, A2, A3, T0 to T7, S0 to S7, T8, T9, right? They're basically all the same. The only difference between all the registers from AT all the way down here to the S registers, to the T9 registers, all of them, there's like 20 registers. The only difference is compiler conventions. By default, compilers will compile code so that a function always returns its value in V0 and V1. If it's like a big value, then you need 2 return registers. And that the function arguments are stored in A0 to A3. And that T0 to T7 and T8 and T9 are like temporary value registers, just throwaway registers you can use whenever you want. AT is also a throwaway register, which is why I used AT right here. But it's basically it. S0 to S7 are also all the same, like engineering-wise, but compiler-wise, you use them differently because the S registers most compilers expect the S registers to not change when you call a function. Because when you call a function, the function is also going to modify all these registers, so you don't know which values have changed, so you would need to store all of them. The S registers allow you to avoid that. K0, K1, don't touch those. They are like hardware important, just don't bother. GP means global pointer is what this stands for. Some games use this for S data, but it's technically the same as all these registers. SP stands for stack pointer. This is where your stack, this just points to a random memory location usually. That's like what the compiler does. And you can store like variables on your stack here. And then FP, frame pointer, looks like this game doesn't even use it. Also kind of a useless value. That is basically the same as all these. And RA is a very important register. RA means return amount. This is whenever you call a function, the hardware automatically puts a pointer to your next instruction into RA so that you know where your code needs to return to. Saves us a lot of work. Okay, we should also go over the floating point registers here. These are some more special registers. These can store floating point numbers from special floating point instructions. We'll go over these in more detail later. For now, just remember, only use the even numbered ones. Don't use the odd numbered ones, they're for doubles. The even numbered ones are for singles. Basically, when you store a double in F0, it's going to overwrite F0 and F1, right? So just don't use F1 ever, unless you have some very special conditions. But most N64 games will just crash if you use F1 or F3 or F5 and so on. We should practice with this, and I think the best way to practice and understand how assembly works is to take a C code and to just quickly convert it into assembly code. We don't need to do this optimized, we just have to go over it once, and then you will see a few instructions. So for that, I'm going to use my A tends to S code here. All right, here I have the function converted for you guys into assembly code, and let me go over this. First, I mentioned calling conventions before. The calling convention on most compilers is that the first floating point argument right here is going to be stored into F12, and the second floating point argument is going to be stored into F14. So that's why this is going to be our assignment here. These variables don't actually exist in the game's memory. They only exist in a register. Now we have our line abs_y equals abs_f from y. There is a very good abs instruction here, absolute dot single precision float. F0 is what we store it into, and F12 is where we get it from. So now F0 is going to be the absolute value of F12, which is exactly what we have noted here. And basically this register F0 now holds the same thing as our C variable abs_y. Next, we do the exact same thing with the abs_x variable. And then we compare abs_x over abs_y. We don't have a bigger than function in MIPS assembly, but we have a less than function. So instead of doing bigger than, we can do less than and then invert the value, right? So this means compare less than single precision float, F0 and F2. So if F0 is less than F2, it's gonna set a value to true that we can later read. This value that we later read is actually happening right here in this branch coprocessor 1 true. And if it is true, we go to don't set the value. If it's not true, we set our T0 to 0. And if it is true, then this assignment that we've done here is gonna, we do this, we jump here. So this assignment is gonna stay. So basically our T0 is now the same as our C variable x over y. Next, we have an if x over y thing. We do one thing, otherwise we do the other thing. So how do we check if the condition is true? Well, like I said before, we have our special register R0. So we do branch equals T0 R0, which is basically like an if T0 is 0, right? It's kind of like the opposite of this, but it's easier to do it this way around, I find. So if this is true, we jump into this part of the code. If it is not true, we execute this part of the code. Not being true means this part runs. Being true means this part runs. They're kind of inverted in this, but it doesn't matter. It's the same code. Now we have our two variables here, 1 and 2, that we want to assign. So the easy way to assign a floating point variable is to just run the mof.s function, which moves the value of F0 into F8. And here you see something weird. You might think, hey, why is that mof.s happening below the BQ R0 R0? BQ R0 R0 is basically an unconditional jump, right? Like R0 is always going to be equal to R0. You can put any registers here. It's just convention to do it with R0. Well, the thing is, on the MIPS core processor, on the MIPS CPU, when you do a branch or any kind of jump, you're always also going to execute the function after it, because it's in a delay slot. This is just like a thing on how the hardware is designed, because designing the hardware like this was a more efficient hardware. So by moving this into the delay slots, we can like avoid having to do something like this and then a knob, and then we'd have like an additional instruction that maybe takes away space or whatever. So this is kind of a neater way of doing it. We could have done the same thing up here, but I thought this was nicer to show it here. Okay, now we have this part of the code done. If 2 equals 0, I didn't put that part into the code, it doesn't matter. We don't need that, hopefully. Just ignore that. Now we have our division here. If we want to compute this part, right? Atens equals garctan table rf, which don't worry about rf. Rf is just an assembly macro. Yeah, 1 divided by 2 multiplied by 1024 is what we need to do first. We need to do the brackets from inner to out, obviously. So let's divide our variables 1 and 2, f8 and f10. For that we do the div.s instruction, division.single. Like I said, all these instruction names are super self-explanatory. It's like really easy to just look at an instruction table and know all your options. So we divide f8 by f10 and store the result in f6. Seems good. Now we have this part finished. Next we want to multiply it by 1024. Now there's something weird with 1024, because as you can see in the next line of code, I'm getting the number 44800000. That's because this is in floating point format. If you don't have a floating point converter, this is a pretty easy way of you doing it. I like to use this one. Just put 1024 in. And as you can see, the hexadecimal representation of the number is exactly this. We have to do this in a general purpose register. We can't put the number directly in a float point register. This only works on general purpose registers. And then we have to move them to the floating point unit, which move to coprocessor 1 is right here. We move the 80 into F4. Yeah, it's kind of fucked that usually you'd always have the register that the result is in first, and then the register that you get the arguments from second. But the MDC one is just weird like that. You just have to put that. I do a knob so that the floating point processor is like one cycle to get the number in. And now we multiply our F4, which is 1024, by F6, which is the result of the division, and we get the inner part of the bracket. Next, I showed this before, the round.w.s and the mfc1 macro is from our inner function call here. Don't worry about that, it's not really part of it. And we get in T1 our array index that would be right in here. Now the thing is, our array is not a single byte size, right? It's a 2 byte wide element in here, right? If you click garctan table S16. So our index is only half as big as we actually want it to be. So by doing SLL, shift left logical by 1, we just shift the entire byte value by 1 and add a 0 at the end, which effectively is like integer multiplication by 2. And now that we have our array index, we can get like the RAM value of the arctan table right here. You see we do this in 2 parts, again, like we did earlier. And we add 80 and T1 and store it into 80, right? So this basically adds our array index to the start of the array pointer and stores it into 80. And then we can finally load from arctan table, and we have this line of code finished. So yeah, that single line of code ended up being all of this. Assembly is kind of verbose by comparison to C, but it gives you a lot more control over how you want your code to work. And you kind of don't have an option. If you actually want to reverse engineer N64 games, you're going to have to read a lot of assembly. unless maybe someday in the future AI tools will have us covered and they'll be able to somehow just unassemble assembly code. But I don't know if we're there yet. Alright, after finally having done all that, we have a bit of floating point bit manipulation. So this line of code is a little hard to read, but basically what we do is we get the hex representation of the float instead of the value of the float, which means we can just do MFC1. This puts the float value directly into the general purpose register here. It's like the opposite of MTC1 that we did here, right? We don't need to convert between formats here because we want the exact representation. If we wanted to convert between formats, what we could do is CVT, which means convert, to word from single F12, F12. Doing this would make our F12 like an integer value. So instead of 4480, that would just be like 1024 now in the register. Well, if we did it with that number, but this is our X, so yeah, actually this is our Y. All right, next we see we are shifting this by 16 bytes to the right, which means we use the shift right logical instruction. Store into T3 the result of T1 shifted by 16 bits to the right. And then we have an end by 8000, which is this one here, and the T3 store in T3 the value of T3 ended with 800. Again, just like already before, and with an immediate value. Super self-explanatory. Next we got a similar thing here. We got the floating presentation of Y XORed with the floating presentation of X. So we have our MFC1 T2. T2 is now our floating our bit representation of the float. We XOR it with T1. We cleverly have not overwritten T1 from here, so we kind of save like an instruction by just, you know, using T3 all throughout this code instead of using T1. And then the RCRL17 and the with 4. Last, we have the plus sign here, so we just store in T2 the result of T2 plus T3, and that's it. Now we move on to this part of the code, which is this last bit here. If offset and 0x4000. Alright, to evaluate that, we first need to end T3 or T2 with 400 because T2 is where our offset is stored right here. We can overwrite T3 now, we don't need it anymore. We have that register free. We could probably also overwrite T1 or whatever, or 80, but I just figured we use T3. If this is not true, we go into this part, which conveniently this time is also the lower part of the code. If it is true, we do this part of the code. We still have our X over Y in T0. We have not overwritten that. So if that is not true, no, if that is true, we go to return now because BNE branch not equal. If T0 is not 0, we go to return now. And then we simply invert sub V0 R0 V0, so store in V0 the result of R0, which is always 0, minus V0, and then we have our add by 0x400 to our offset. We luckily have not overwritten T2, and then we simply add them together, just like at the end of the code here. Second branch, basically the same deal. So you get it. It's just really simple, rudimentary, basic instructions that we do one after another to manipulate memory and like variables. And in the end, we can do any logic we want. We can assemble whatever we want out of this. It's Turing complete. All right, now that we have some basic understanding of assembly, we also have to do the opposite of it. This is going to be a lot harder, logically speaking. You don't need any knowledge for this. You just need a shit ton of skill. This is the opposite because we are turning assembly code into C code. This is going to be what you're most likely going to be dealing with when you're actually working on reverse engineering games. Because you will have to be able to understand an assembly code and turn it back into your C code. And because compilers do some fucked up optimizations, some messed up stuff that no human would think to do, There's no rhyme or reason to anything they do. So this code is not written to be readable by humans. This code is just insanity. And let's go into it. So this is a function. It goes from here all the way down here. This is just like not even 10 lines of code. But this is going to take a while to decompile into something that we can read. So first we see we have f12 and f14 used without them being initialized first, so we can assume that this function takes at least 2 floating points as our input, and we see that it does like an f0 thing. F0 is, by calling conventions, the return register for floating points. So we know the function is float unknown, and then there's like a float a and a float b. And we have something that we return. So we can already, on C, we can just like declare a variable in the stack. This doesn't actually exist in the assembly, but it will compile the same. So we have a return value, and we will return red. This much we know about the function. Now we have c.lt.s, compare less than. So we already know if a less than b, right? Because we have a2 first. No, actually, if bc1f, so if a is not less than, so not this, we do something that we branch to. Otherwise, we do the normal code. Oh boy, this doesn't have inlining. Isn't that beautiful? I guess I can manually inline. Oh my god. I'm sorry that this is barely legible. Alright, so BC1F. If this is less than that, we jump to ED58, which does a compare less equal single. So F14 and F0. We don't have F0 set yet. F0 gets set here in the delay slot. So this is always being set, which means red equals F12 and F18. F18, okay, that means we have more arguments, F16 and F18. So let's see, right, because F18 was not initialized anywhere, so we already know there's at least 4 floating point arguments. Red equals A minus D. And we go to EF8, F0. Compare less equal F14 F0. So if this is not less than, if this is B, I guess, less equals red, then we have another piece of code. We go to 4.8, which is right here. Branch coprofessor 1 false likely. Okay, that's just a branch prediction thing. We don't need to. Actually, this, I think the branch prediction doesn't actually have the delay slot, so that is neat. If this is false, so we do this. We move F14 into our return register. So red equals B, semicolon, and otherwise we just return red. Perfect, so we don't need this part anymore. We are done with the first part of the code, hey! Alright, next we have add F0, F12, and F16. So F12 is that, so red equals A plus C. What was that? Compare less equal F0, F14. Okay. Where is it here? So this is actually the same thing. Cool. This is the exact same code as this part, just the if condition is different. If not F0 is less than F14, red less equals B. Wait, that's the same one. No, it's inverted. Okay, okay. Nice. And we did it. That's what this function does. Might be a bit hard to read, so let me show you what the actual version of this function is. It's this one here. Approach S32. We have our current, we have our target, we have an increment, and we have a decrement. And if we're less than the target, we increment. If we're more than target, we decrement. Which is what this does, just in a whole lot less readable way. But you could piece it together from here. I think this is still a lot easier to read than this. So that's kind of how you can evaluate assembly code and try to figure out what it does. Maybe to make this a little more clear, let's compare these side by side, the real version and our decompiled version. So we can see that red gets overwritten right here anyway. So we might as well move it into here. And red is being calculated from A minus D or A plus C, which is current plus inc or current minus inc, right? We just have this written down in a bit of a weird way because we don't have the plus equals here. And we have all the branches turned around, which is also not very helpful here, but that's just how MIPS assembly does it. But you can see by going between these back and forth, if you just made a few little changes, they'd be the exact same. And I'm pretty sure that to GCC, both of these functions here compile the exact same. It can't tell a difference between these. It's just that this is just really unreadable. Let's say we want to make it so that the blue coins give us more, the blue spots give us more coins. Let's toggle right breakpoint here. We'll roll our 5. I guess the RNG seed is the same, so we get the same number. And somewhere here, it should do a right breakpoint. So here you see SH-V0-0008 A0. What does that mean? SH means store half word, which is just 2 bytes. V0 is the register we store from, which, as you can see right here, 03E8. That looks like our number plus 1. To 0008 plus A0. What this means? A0 is just 8 short of our RAM address, and the 8 is just what gets added, right? So basically, this just stores whatever's in our variable V0 here, or register, as you call it in assembly, gets stored here. We have an addo instruction here, which means add unsigned. V0, V0, S0, which means V0 becomes V0 plus S0. And if you check S0, you can see it's 1. Now, if we wanted, it looks like it always adds 1, and it does this 3 times, right? Because we landed on a blue spot, it adds 1. I'm guessing if we press it go again, you see, it did it again, right? So it does this 3 times. It adds 3 times 1 coin. So if we wanted, we could just change this thing here to, instead of adding 1 thing, to always add 2. Or we could see when it stops adding this number. So let's just go for that. Right, okay. I've been doing things without explaining it. Basically, any function starts with an addu, sp something, which is the stack pointer. Basically, in assembly, when you want to call a function, you have to decrement the stack pointer, and then you just store everything, every temporary variables onto the stack pointer, right? The stack pointer is just some random piece of memory, and then you execute your code, and then at the end you restore your stack pointer, right? You see here minus 0x to 0, and then right here you see the sp plus 0x to 0, and you see the RRA. RA means return amount, so every function will end with a JRRA on the N64 and the stack pointer restore. Some functions don't need a stack pointer modification, but you know, that's not what's happening here. So we see, this is the function I called it. I don't know what the A1 means here, but that could be our suspect. So let's just go to this line of code, 8005564C. Change it to a 2, see if that doubles the amount of coins we get. It just might. It's very lucky we actually land on a blue space right away, otherwise this would have taken eternities. Oh, actually I have 999 coins. How would I even be able to tell? Let me just turn the game share code off. Do that again. Remove this breakpoint. There we go. Blue coins give double the coins. Let's make that a game share code as well. Which, you know, this time we only modified a single byte. It would be 800556 4F0002. I don't want to start a minigame, please. So let's note that down as well. Blue spots give 6 coins. This one. I'm sure this has other effects as well, but for the sake of this tutorial, this is enough to understand what's going on. Alright, well, now you've learned the basics of how to use Project 64 Debugger and how to make game shortcuts. Next, what if we wanted to make a more complicated change? Let's say we want to make a game shortcode that lets us actually cheat in-game dynamically. Let's say we want to make it so that if you hold the L and the B button while you roll your die, you always roll a 10. You could really mess with your friends if you played with them on your Mario Party 64 cartridge. For that, we will need to load our own custom code into memory, and that will allow us to read some variables in runtime. How do we load our own custom code into memory? Very good question. So let's go to LAMASM, and actually let me show you the boot up process of LAMASM properly once. We boot it up, we open the ROM, we pick our Mario Party 64 here, we press F6 and F7, and there we go. Now every N64 game, when you boot it, it jumps to whatever code is at the address 10000, which is right here. And if we want to load our own custom code, this is like our best bet, because we know for sure that this is going to be a piece of code that will be reached. And if we can tell the N64 to load more data into memory in this point, then we could later use that additional data to add more code that will allow us to add more complex behavior without, you know, having to do any weird things like shortening a 16 assembly code, which can be a lot of work. Additionally, I want to mention that if you do load your custom code like this into your game's memory, you actually can use the MIPS GCC toolchain to compile it directly. But that's kind of a weakness, so just go with the assembly. And next, we also need to find some empty memory and ROM space to actually load data to and from. Finding empty ROM space is super easy because every N64 game is padded to like a nice even number. So let's just go to 1FF0000. You see it's all Fs. Let's make that a note. Load code from 1FF0000 to 1FF1000 maybe. Maybe that's enough. I'm not sure how much code we actually need. Let me check my notes because there's more stuff I want to do at the end. Okay, we'll actually be loading up until 1FF000 because we're going to import some custom models later, and they will require a lot of memory because they will be very high poly. All right. So how do we actually go about loading our custom code? Well, on this website here, they actually have a pretty good DMA write RAM method that we can just copy paste. We'll just need to be a human compiler. And we'll also need the space to do this somehow. Now, the easy way to do this would be to just take this code here, compile this code into write whatever this is, and then jump into our own custom memory segment, and then take the code that's right here, all stuff, and put it exactly where we just loaded, right? So that way we'll be loading code, executing whatever Mario Party 64 is usually doing, and then jumping right back to where Mario Party 64 would usually be. Completely undetectable, and we have our RAM. But I think it's a lot cleaner to look at the existing assembly code and shorten it in a way that our code fits here as well. I think that's a lot cooler. So if we look at this code, we see a lot of weird things. Let's just go by this one by one. Louis T0800D loads the value 800D0000 into our T0 register. Edu T0 adds the value CE50 to this number, which is actually a negative number. So now our total number is going to be 800CCE50. Louis edu another again. Then it stores 0 to whatever this parameters is. It stores 0 to whatever this parameters is plus 4. It adds 8 to this parameters here, which actually it's not even a parameters. Subtract 0 from it. And if it's not 0, it just keeps storing zeros. Yeah, so it looks like this is just writing a bunch of zeros for however much this size here is. Right, so basically this is just resetting all the memory of the game to 0. Okay, fine. Looks like we need that. Next step, it gets this number here, 80000460, and then it jumps to this. And we see this is right here. So actually, if you look at this, we don't need this, we don't need this, and we definitely don't need this. Very nice. This gives us a lot of space. Let's just take this here and move it here. Take this here. Oh yeah. Whenever you write a line of code, you're gonna hear the Windows error sound. Get used to it. This program is from 2008. It's the best you're gonna get. Alright, let's be a human compiler and compile this code into something that our N64 will understand. So our first line of code is while DMA_rec status and DMA busy. DMA_rec is at A4000, so let's just load it in. Louis AT A460, and then we read the status number, which, if you look at the site, status is right here. Let's count the bytes: 0, 4, 8, C10. LW, what's a good register to use? Actually, let me use A0 here. W800010. It doesn't really matter which register you use, I just kind of like notes I'm referencing. And we have the DMA busy. DMA busy is defined to be 001, so we take $80 and actually I think no, this is fine. So while this is going on, we just keep looping back with our BNE instruction. Right, I should explain. Andy is gonna do the end instruction here. It's gonna end with the number that we put here, 001. 001 is this. BNEZ, branch not equal 0, 80. So while 80 is not 0, we jump back to 1030. These are relative branches, so we don't need to put the parameters here, which is right here. So basically these 3 lines of code will just stall the code until DMA busy is no longer being written. Next we want to write to rampy, as this does right here, to whatever parameters we use. Right, we haven't decided on the parameters to use yet. Well, we don't really know what RAM is free in Mario Party. We could look into the game. We could play through the entire game and like figure out which RAM is unused. But we're on the N64. We can actually just go into options and right here add the expansion pack. That's the easiest thing to do. You can do this with most N64 games. So load code to 80400000 to 8040F000. That's the easiest thing we can do. Since we already used AT before at A0, doesn't really matter what we use. Let's just use A1. A1 to 0 from A0. As you can see, rampy is like right here at 0. Rompy is gonna be at 4. Our ROM pointer is FF. It's WA10004. A0. Oh god, our space is getting very tight. I'm sure it will fit. Size ROM RAM is length -1. Our length is... oh, well, it doesn't matter. We can just go with 1. Alright, I guess we load like until FFF now. SWA100. Where does this go? Size ROM RAM. Oh, this goes to C. 0. And then lastly, we have another one of these. We don't need to return anything, because what will we need to return it for? And now we just stall again. So LWAT 010 from A0, maybe an EAT R0 054, and NDAT. Yeah. So you might notice that I'm doing the BNE before the ND this time. And that is because in MIPS assembly on the N64, we have something called a delay slot. Basically, every time you do a jump instruction, the instruction after the jump is going to be executed as well. So had we swapped these two around, then the add USP SP would be happening over and over, and our stack pointer would like go all the way down in memory, which is not what we want. This way around, we have one ND too much, but who cares? Like, we don't need to care about that. So what if we have an ND too much? Let's save our ROM, just to make sure that it worked. We are going to go here. We're gonna write, let's write Handmade. I'm sure Upna will like that. And yeah, open our ROM, see if it's actually in memory. Did my emulator crash? This emulator is sometimes not very useful, not very stable. You will experience that if you work with this a lot. It will sometimes just crash when you open this. Oh, it didn't this time. That's good. All right, let's go to 80400000, and it says Handmade right here. That means it worked. Our code is in memory. We have successfully acted as a human compiler and compiled the code into our ROM. And yeah, like I said, I mean, the space here was really tight, right? We like just managed to scrape by. Maybe there's some place here where we could still save an instruction. But like I said, if this space is not enough, instead of doing it this way around, you could just like have the sort snippet from here to here, and then here, instead of, you know, starting the normal code, you could just have a jump instruction, right? Like I could just, instead of this, I could just do $80400010, and the code would jump right here. And you see all this empty space with nothing in it. This is where I could just do like the normal boot up code. And if we did that, then practically we have infinite space. But, you know, let's not save that because that would ruin it. Alright, next up. Now that we finally have our space where we can write any code we want, we're gonna rig the dice roll. Let's figure out where the variables for the dice rolls are, just like we did with the coins for before. We gotta have to boot up our game here. We actually need two variables here. We need the controller, and we need our dice roll. So I think this should work with any player's dice roll. So we can just use the NPC dice rolls for this. So I can already tell you that finding this number is going to be difficult, because there's visuals, there is like physics associated with it, there's a timer that ticks down, but let's just go for it. Let's just try to find it. So we have 8, right, and now it goes to 7. So, and now there's even more. And even with all these, none of these are guaranteed to be the actual value here, right? So what looks likely right now is that It's this number here at 800D62D3. Let's just set it to 8, see if Yoshi works further. I did not think I'd be sitting here today watching a computer fail at this minigame. So anyway, what we learned from that just now is that the number that's being displayed is not actually what the character is going to move. These two seem to be separate variables, which is going to make our life a lot harder. So we're going to have to, again, find the variable as soon as they roll. Like right there, she gets a 9. Search for 9. I don't know if it's still a 9. It might not still be a 9 anymore. So we're just gonna roll for the next player and then see if that's stored anywhere. Last search did not yield the result because accidentally that was only the visuals. So let's just carefully write before they take the step. Might be when this variable is actually relevant. Like, we're down to a few of them. It's gotta be one of these. What if I set this to 8? One of these is gonna be her actual movement distance, like I'm sure. This one's just changed to a 34, and this one's to 0. It's not either one of those. We already know the visuals, and oh, this looks promising. Can we give Peach an eternal turn and just make it go around? Yeah, I think we found it. It's at 800 F3 FF3. Next step, let's figure out what's actually writing to this. And this will be where our entry point is. So right here, we store our V0. We could probably just overwrite this with something else if we wanted. Where's the V0 even coming from? This function here? I kinda hate that it's already saying the 9. Like, the number has to be coming from somewhere. Let's figure out where it's getting this number from before it starts writing to the actual movement distance. Which, you know, you can see right here, it starts the V0 here. And it does the jaw right here. So it stands to reason that this jaw returns the movement number in V0. And we can see it loads it from somewhere along A00D. You don't actually need to understand any of this. You just need to see, oh, 800D plus 6 to D3. That's actually where we were before, 800D, 6 to D3. And I bet along here somewhere is where it stores all the movement distances. Oh, but it adds V0 to that. V0 is 4, 4. 4, 4 plus this. We can just use Google for this. 0x this, 0x 4. That's the easiest way to do the math. 800D6317. So right here, that looks exactly where the number that she rolled is stored. Let's figure out when it's written. We found the exact spot. You see it right here? V0 says 9. It's like solving a puzzle, you know? That's the beauty of doing this assembly. You solve a little puzzle and it's really fun. Alright, so yeah. Right here is where it stores it. And if we go into this code and we overwrite this code with our own custom store, we will be able to just do whatever we want logic-wise. Our first step should be writing down a few numbers here that we just data mined. We don't need this anymore, just so we have an easier time finding these later. So we know that of 800 D6 3 1 no 86 D6 2 D3 stores rolls here question mark and 800 D6317 player 2's roll, something like that. And at 800405660, no 564, stores the number that was rolled randomly. Now, if we want to modify this code here, the easiest way to do it would be to find the code in memory, in the ROM. So we can do that by just 040560. And this is our code here, so we can just open the ROM. We can press Control F, hex numbers, which by the way, I use HXD. You can use whatever hex editor that you prefer. But if you just look for it, 808 01 01 5B 82 02 0003. Oh, I only looked forward. Oh, we have multiple hits. It's not good. Which one of these is ours? The second one. All right, we get our friend LemASM. Just so we can actually see the proper assembly instructions here, 41160. And right there is where it stores our V0 to 0003 from S0. Now, the easiest thing to do is to just, this is how you write code in Kaze Emanuar, by the way. Press .org, and then you do like where you want to write the code, which is 41160. So instead of the jump to 4056C, we will jump into our own code. Let's call this hook. J$400010. SBV0 to 3 from S0. Okay, we don't need that, so let's just add a knob just because it looks cleaner. I don't know, it doesn't really make a difference. I'm going to overwrite that number anyway. And our custom code is going to be at FF0010, right? You see, we read the code from 1FF0000 to 8040000. So if you add 10 to this number here, or if you add 10 to the RAM address, we also need to add 10 to the ROM address. And this is where our actual code is. So we're gonna have like manipulate the dice roll here, and then we're gonna do the same line of code 0003 from S0, and we wanna end at 4056C, just like the original code does. So we copy this as well, right? And now we can just rig our dice roll here, and then do exactly what the vanilla Mario Party game does, and no one will know a thing. Next, we have to find out where our controller is. Now, finding controller variables is actually super easy. We just pull up the N64 controller values on Ultra 64. Unfortunately, I could not find the file online, but I do have the file on my PC, oscont.h. I can link that as well. That's in the Mario 64 decomp. It has a lot of very useful N64 resources. Either way, next is going to be finding out which buttons on the controller I actually pressed, so that we can make it so that if you hold B and L, your dice is always going to roll a 10. So let's unpause this game for a bit. We're going to use the memory search again, because we actually need to find the controller in memory. Come on, stop breakpointing. There we go. Memory search. So since there's more than 8 buttons, we know it's at least an int 16. And let's just hold the L button. So the hex value of the L button is 0020. And let me just pull this up here so you can follow along. Let's press the B button. The hex value of the B button is 4000. Let's press like the B and the A button together, which will be C0000. And holy shit, we have a lot of results, and all of them look to be exactly the controller buttons. You see that? I press B, they all go to 40. Oh, one of them did not. Let go of them all, they all go to 0. So one of these will definitely be sufficient. Doesn't matter which one we pick, let's just pick the first one in the list. Who cares? If this one doesn't work for whatever reason, we can still change that. So, oh shit, we don't know which registers we are safe to use, which kinda sucks, because, you know, this code here could be running from everywhere. Oh, that's not where our code is. Let's just go on to our code. So, since this code could be running anywhere, we don't know which one of these registers is safe to use. If it runs to this, okay, there's a JAL next. So we know we can't use S1, because S1 is being used here. Other than that, all of them seem safe. So let's just use 80, because 80, who cares? 80 is usually the register you use, it's like you are every man. 800D. And just because we might want to switch the RAM variable later, I'm gonna do something slightly inefficient and do 1170 like this, which ORs our 80 value here with 1170, right? So now the value of 80 is 800D, 1170, and we're gonna LH from 80 at 0000 80, and we're gonna check if it's equal to L and B, or rather we're gonna check if both L and B are pressed. It doesn't need to be equal, because if we check for equality, then because pressing A from, you know, hitting the dice is gonna mess with it. So we're just gonna do an ND here. ND 80, 80, 4020, right? 40 for the B button, 20 for the L button. And since we can use whatever register we want, let's do add U A0 R0 4202. Right, now we have 4202 and A0. We have ended our controller value with 4202, which means that if they're equal now, at least the L and the B button are pressed. So let's do BNE 80 A0. If 80 is not A0, we go to don't cheat. Let's do an up just for our delay thing. Also slightly inefficient, but we do not care about efficiency right now. We just want to cheat. And if we do that, we modify the result of V0 by adding 0 and the number 10, hexadecimal A0, and that will give us our cheat code. Let's assemble it. File has been assembled. Let's open our game and see if we can successfully cheat at Mario Party without any of our friends being able to notice. It's gonna take forever to boot up again. So this technique of just inserting code like that is the most common way of making like an assembly hack, and it's also the easiest way. It would be a lot harder to like shorten the code to like also allow your own custom code to be in there. That will require properly understanding all the surrounding code and, you know, optimizing it a little by hand. And that's usually what I prefer to do, but that is absolutely not reasonable to do. Also, now that I'm thinking about it, we have cheated this in a way that holding L and B will also give other people a 10 when we do it. So that's nice for our testing, and that like lets you mess with people extra if you want that. Imagine playing this with 4 people and you just let everyone roll a 10, and as soon as they think, hey, the game's bugged, we only roll 10s, you stop holding L and B, and you just start rolling whatever. And then you do it again as soon as they're no longer suspicious of you. It's not gonna work here though. These are special dice, because 2 people can't roll the same number. Alright, L and B. She got a 10. Looks like it worked. Let's also test not pressing L and B at least once. Let me make a save state here, just so we definitely know, because of the fixed seed thing. Roll to 9, hold LB, roll to 10. It works. We have cheated at Mario Party. We can now beat all our friends with ease. Now, the last thing I want to show you guys in this tutoring thing is something that's a lot harder, like assembly coding wise, and it will require a lot more effort. And that is making your own custom model replacement. So for this, I already have a model beforehand, which is a gigantic, you will see, it's a very stupid model. I have saved this file on my desktop as Mario. Right here, this is our model. Isn't he beautiful? Oh boy, look at those polygons. Awesome. Yeah, we will be importing that into this game, and then we'll have our own custom model replacement, which, that's kind of hype. You can just put your own custom models in any N64 game you want. So for that, we'll first need to find the Mario model in memory, obviously. Technically, the correct way to do a model replacement would be to decompress the ROM, replace the F3D inside the ROM, you know, like really go all in on it. Now, well, technically, we could be figuring out the decompression progress. That would take at least like 10 hours. That's absolutely not reasonable for us to do. So instead, what we're going to do, we are going to use a very, very hacky method. And that is going to be looking for this model in the game's memory. Look for the model memory. We dynamically override it during runtime to point to our own model. So for that, the first thing you need to do is find a way to identify the model in memory. And then next up, we need to find a point that is being done like once per model load, where we can actually just scavenge the whole memory to see and find the model. We need like an identifier for that, and then we override it. So how do you find the model in memory? Well, that's a very difficult thing to do. But with a bit of knowledge of how the model format works, we can figure it out. So Mario Party uses a microcode called Fast3D, which is like the successor of just Fast3DX, which is the successor of Fast3D, and it's very similar to Fast3D. And basically, these are like comments that you feed to the processor to like draw triangles on it. And we're going to be using the texture comment here, which loads a texture, to just look through the entire memory. And if we find like the texture that is for Mario, then we know this is it. Now, the fastest way to do this would be to like write a code and have this code be like in the ROM itself that overrides like 15 pointers for you at once. So you could go through these quickly. Or you could do some sort of binary search, because let's be honest, there's only 10 models on the screen. So if you just like go to the middle, change one, and if that's like not Mario, then go to somewhere else until you find a set. We want to replace a set, you would also find it. That's actually how I did it, but I've done it for you guys, like to save you time. I can tell you the model is right here, and we can confirm that this model is right here by changing this to a df, and as you can see, the set disappears. The df comment just ends the display list. It just says stop drawing any triangles. And we tell it to stop drawing any triangles, and it does not draw the head. Next up, we need to find a way to identify this model. There's a problem here, because this model is dynamically just like repointed in memory. There's nothing in this that we can really identify as anything. Because this is just comments that tell you load this texture, set this render mode, you know, that's like the same for all the models. But one unique thing about Mario's model is this texture. Nothing else uses Mario's texture. So if you look at the texture loading comment, let's just check this one out. FD100000, 81, 1F, 0F20. And we compare to this here. What could that mean? Well, the BBBB here is the texture pointer, segmented address of texture. So yeah, this is just like a RAM pointer, which I guess is also a valid segmented pointer. So if we just go to 801F0F20, we can see if we change this texture. If we change this texture, Mario's face changes. Beautiful. So just made him slightly more orange. So that's what we're going to be taking advantage of. We're going to be looking for this number in memory. And well, here's our general outline. Find texture in memory by looking for FD E1418B. Add 0xCB0 to the texture, Y0xCB0. Our display list is right here at 801FDAE0. And our texture is right here at 801F0F20. And if we subtract these numbers from each other, we get CBC0. Right? So now we can say, hey, if we find the texture is right here, or at any address for that matter, and we add CBC0 to the texture, then we know we are exactly where Mario's head polygons are. Because they're always going to have the same relatives offset from each other, because they're going to be loaded at the same time, obviously. Right, so we find the texture, we add CBC0, we write a pointer to our own model into the memory, and then when the model was overwritten, we go back to our texture pointer here, which is right here. And we're going to set the alpha bit, which is the lowest bit here. Instead of 8B, we're going to say 8A, which doesn't make any difference because Mario's being rendered opaque, right? But we just set that there just so that next time we run the code, we know, hey, the model has been overwritten. All right, so what's missing here? Well, the first thing's missing is we need to actually find a point where it makes sense to read the code from. Because if we do this every frame and we iterate the whole memory every frame instead of just preloading the whole transition, it's not gonna be like, it's gonna lag the whole game like crazy. It's gonna be impossible to work with. So how do we find the hook? That's a difficult question to answer, but I mean, that's what I got our debugger for. We're gonna be doing some research. So we know that this display list is dynamically generated, right? So we know that when the model is loaded, it is being written to. So let's just set a write breakpoint here. Let's exit out. Let's come back in. And we should be able to find something. That is just clearing memory. We don't want that write. This is not actually writing to us, but this is a DMA copy. This is just loading data from memory to the ROM, to RAM. As you can see, the pointer is just, the pointer was nothing, but now we have a thing that like slowly overwrites the pointers one by one. Right here, you can see like it's slowly writing the model into memory. Right, as you see, the red dots appear. There, 0 appeared, and F5 appeared, 0 appeared. Yeah. So we can tell this is where our model gets written to memory. So this is a good candidate for that, right? If we find what's calling this function and just go there, then we have a good lead. Let's just verify that this function is not being called a million times. It is being called a million times. Cool. 8, 9, 10, 11, 12. Oh boy, that is not good news. It looks like this function is always called exactly 12 times. Sorry, there's a strange cat at my window. I don't know what she wants. I don't know this cat. I did not mean to get distracted. Yeah, so if this has been called 15 times, we can't just go for a RAM 15 times. That is way too much. So if instead of this, we had something else that we could do, like maybe there was an outer loop to this, we could try and use that. So this kind of looks like an outer loop to the function above, but it's also called 100,000 times per frame. Oh, but it stops eventually at least. Alright, let's exit this again, put a save state, and eventually I'm sure we will find a good place. We just keep going out and out and out until we find a good place. So again, just like before, if we locate the JRIA and the add USPSP, we will be able to pinpoint the location of the function that called our function here. This is not what we want. We want the JRRA. Let's make a few notes here just for debugging. So runs after model is being repointed. And then output loop. It's always good to like keep documentation like that, because if you ever get confused, you can just go back to where you were. Writes the model, one call, 2, 3, 4, 5, 6. 6. There's 6 players. Perfect. So this runs whenever a player model is being loaded, I'm guessing. This is a good enough hook. Alright, so what exactly do we do now? We're taking this JAL here. So we have a hook here. .org. We don't know the address yet. Hook 2 is just, I don't want to use the same name as before. Overwrite JAL at 800FBC34 with a... Should we use a JAL? Yeah, a JAL is fine. Unless this function stores argument onto the stack pointer. Okay, it doesn't. And just to explain real quick, we have 3 argument registers in MIPS, right? A0, A1, A2, and A3. That's 4 actually. And what happens if a function is more than 4 arguments? We need to store more function arguments on the stack. So that would be stores to the stack pointer around here, but there aren't. So we are free to JAL our own function and then JAL again without changing like the registers. So we're all good doing that. So with the JAL to our own function, we're just gonna be at 804000D0, because we're gonna write our own code to 1FF00D0. Because if we look at our ROM, 1FF00D0, there's some nice free space here. And then our own custom model is gonna be stored at 1FF100000. I said a few too many zeros, but you get the idea. Alright, same trick as before. We use the memory search to find our thing here. Something about this memory search is just being really fucky right now, but that is fine. We can read just enough to do our thing. 0C005D 302405069D. Let's see if we can find it. Oh, there are multiple occurrences. That is not good, so we need more numbers. 8E030040. There is still multiple occurrences. So our hook is at 0x2C47F4. And we just have a JAL 4000D0 here. That is the most difficult part of this. Holy shit, I'm glad we're done with it. I hate doing that. And we don't need anything else here. Next, how do we do this? Well, we want to iterate the whole memory. So get ready to learn some assembly coding here. While writing this code, I have made the shocking realization that maybe it is not the best idea to write the code while explaining the code, while talking, while trying to figure out how to best explain the code. So instead, I have pre-written the code now, and I will explain what the code does one by one. So we keep our alt hook. Since I did it with a jaw, I also, you know, have to do this part here where let's just go over this one by one. So first we decrease the stack pointer. Why do we do that? It's so we can store the return amount, because when we do call a jaw like this, the return amount is going to be a pointer to this number here, right, to the next instruction. So by storing the return amount here and then recovering it, we know safely where to jump back into the code, which will be the next line here, right? So we do a little in-between stop here, so we can safely store all our values and have this neat and tidy before we call our own custom JAL here, which is our code here down here. I called this function repoint Mario because this is what goes into the memory, looks for the entire memory, looks at every occurrence of the Mario model, and replaces Mario's head with our own custom model here. All right, I want to explain how this works. This is going to take a while, so bear with me. First, in AT, Louis AT, we do FDE1, right? So let me annotate this. This does AT equals FDE1, 0, 0, 0. Next, we do an ORI, right? So this does AD set to FDE1 for an AB, right? Because what the ORI does, it sets these bits here into the lower 4, so it basically just overwrites that. Then we do T0 equals 80100000. That's what the Louis does. It basically just sets it to this number plus a bunch of zeros. T1 equals 80400000. Now, obviously, we need this to find the texture later. And why do we need this? Well, this is the start of our iteration. This is the first RAM address where we check if the texture could be there. And this is the end of our iteration. This is the last memory address where we check if the texture could be there. And the reason I'm not starting to check at 0 exactly is because it's just not gonna happen that it's at 0. Like, clearly, the first megabyte in Mario Party is just memory from what we've seen before. All right, next, what do we do? In programmer terms, T2 equals star U32 star T0, basically, right? To explain this, basically we just load the first 4 bytes from T0 into T2. If whatever is there, BEQ branch equals, if whatever is in T2 now, aka the first thing from T0, is equal to A2, aka our texture value that we're looking for, we are going to the found texture label, where we will be doing stuff like manipulate the pointers. If not, also, or T3, T0, T3 is in the delay slot of the branch equals, which means these two instructions will be ran together, right? So this is basically just T3 equals T0. Why would they want to duplicate the value of T0? Well, now T0 is a pointer to our texture, right? Pointer to texture. And we can keep iterating on T0, but we have the pointer to our texture stored now. Very useful. This one is just T0 plus equals 4. Right, and then if T0 is not equals to T1, which is, if it's not done iterating through the entirety of the memory, we just do more loop. We have a little knob because of the delay slot, and then a JRA, because, if they are equal, that means we're done iterating and this is finished. Our iteration is done. If we reach this label ever, that means there was not a single texture we found, which, is fine. All right, what happens if we do find the texture? Well, we, as we discussed before, FDE1 41I8, I am not gonna make as much indentations the first time, right? It's just, this is the difference. We set the B to an A, which is the same texture, just with the transparency set off. So we know that this texture has been overwritten, and then override texture at pointer. And now that we have the texture written out, we will loop over the entirety of the RAM, and we find every display list comment that references this texture. By doing that, we find every occurrence of Mario's model in the memory. So, how do we do that? Well, we load from T0, so T2 equals star U32 star T0. I think you need the brackets, I don't actually know. Next, we set T5 to FD10. This might be familiar to you, because FD1000 is our texture load command, right? So if this is not equal, then we know this is not it. And if it is equal, then we check if the value on T4 plus 1, aka right like this, which will be this pointer here, is also equal to our T3 here, which is, as we discussed before, the pointer to our texture. Yeah, you can see assembly would probably be a lot easier to understand if you had variable names, and I think RMIPS lets you set variable names, which I imagine helps a lot. Either way, if they are equal, then we go to our found texture comment label, which is great. If they are not equal, then we check if T0 is less than T1. Remember, T0 is our current iterator, T1 is our maximum boundary. And yeah, let me explain the SLT comment. SLT set less than, right? Set T4 if T0 is less than T1. So if T4 is 1, that means we are still not out of memory bounds. And in this comment here, we just go back to our texture loop and keep iterating. We add 4 to T4. Why are we not adding 8, right? These comments are 8 in length. You would think we would be adding 8. Well, there's no guarantee that these are actually aligned to 8 bytes. So everything could be potentially the texture comment rather than every 8th byte. And if we don't find a single comment, we are safe to just return. No big deal. All right. Lastly, we subtract. Now that we found the texture comment, T0 is a pointer to the comment that loads our texture. I subtract FF30. Why do we do that? Let me show you in the memory reader. Where do we have our thing start? Oh, I have it in my other notes. I am very sorry about that. I wish I could show you. Right here, we have our pointer to the texture. We add FF30, which means we are subtracting D0. So let's go up 13 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right here. That is where we store our comment to the pointer, right? As we had before, we confirmed that this model wouldn't render if we set this one to df, right? So by just making this our, jump comment, we just jump away from the entire display list and we jump into our own. How do we jump? Well, that's this DE thing here. Let me pull up this again. The jump comment, DE. Okay, it's not on this website. Awesome. All right, I'll just explain it then. The DE display list comment basically says jump to the pointer that is set in the next 4 bytes, right? The next 4 byte is set to 8040 EBE0. If you remember, our own custom segment was at 8040 to 8040F000. So this is just about at the end of our own custom display list. And I just so happen to know that right here is where our custom model starts. That's not right. Oh, there we go. I must have mistyped that. Right here. That's where it starts. 1FF, EB, E0. Right. You probably can't tell this is the start of a display list. How would you figure out that it's the start of display list? It's a bit difficult, and basically that's like a different type of tutorial. If you want to know that, if you start using Fast64, which is how I generated my custom model here, then it will tell you basically where the display list starts. But don't worry about that. I am just telling you it starts at EBE0. And I will be attaching the model and like a few notes as well to the lecture. Either way, we are storing the DE comments to 0 on our pointer, the other one to 4 on our pointer, right? So this makes like the DE 00, 00, 00, 00, 8040, EBE 0. And after that, we are going back to do the function again, because we have no guarantee that there's only one copy of Mars model in the RAM. Probably don't need it. It would probably be like faster by a factor of 10 if we just didn't do this. But you know, just to be safe. And after this, what do we get? We get our stupid Mario. Was it worth it? You know, if you wanted, you could do this with your own model as well. You can do whatever you want here. Alright, it looks like it only worked on the character select. That probably means we found a pretty bad hook. I did this before the recording, and back then I guess I found a better hook because it also worked on the board and during the minigames, and it's a lot funnier. And let me see, I think I have it in my notes. Yeah. In my original version, my hook was right here. So if you just add this code to our document here for Kaze SM, it's gonna also appear in minigames. If you want that, there's that info. And just for the fun of it, let me show you how it actually looks like in minigames and on the board. Right after I hit this real quick 10. Pure skill that I got that 10. Not Mario Party skill, mind you, hacking skill. And then we'll all have a good laugh at how stupid he looks. And you can do this with any character you want, any OC you want. I think there's also a low poly model in the game somewhere that you probably also have to replace. But you know, that would just be the same thing again. I don't need to teach the same thing twice. Look, he's even here. I don't know if he's in all minigames, but I'm pretty sure he's gonna be in some of them. There he is! Beating up the CPUs and glorious 15 FPS slow motion. Fun trick, if you play this game with your friends, you can pause to mess up the timing. Either way, that is the end of this instruction. I hope you enjoyed this. Let me know what you thought. I was your instructor, Kaze Emanuar. Bye bye.